All right, welcome in everyone. Welcome to our Silicon Valley Cambridge Exam Hackathon. I am your lead dev for today's session. And look, we've got our eyes set on the ultimate target mainframe, Cambridge AS and A-Level Mathematics 9709. Let's dive right into this explainer. And honestly, we need to start treating differentiation, and specifically, I'm talking about the product and quotient rules, like a strictly defined algorithm that is just waiting to be optimized. Because let's be real, if you've been sitting down at your desk and treating your exam papers like a random, chaotic guessing game, it is officially time to upgrade your entire operating system. Today, we're going to break down these complex mathematical operations into clean, efficient, code-like syntax. The goal? So you can run your calculations on exam day without a single system crash. All right, let's boot this up. Now, what's really interesting here is this harsh reality straight from the principal examiners themselves. I want you to think of the examiners as the ultimate unforgiving compiler for your code. This quote right here, this is a massive system alert. It basically tells us that a failure in showing your working steps causes a total system failure in your score. You could literally have the most beautiful, perfectly accurate final output, but if that examiner cannot trace your underlying logic step by step, you are going to experience critical point loss. In our dev environment, we call this the differentiation mark leak. And today, we're patching it for good. So, here's our execution plan to clear the examiner firewall. First, we patch the mark leak. Then, we map out the theoretical architecture, establish our execution algorithm, debug the top 3 student mistakes, and finally, deploy the method mark strategy. Okay, Section 1, the differentiation mark leak. Let's debug exactly why so many students see their points drain away during multi-stage analysis. So in our dev team, and honestly, we see this all the time, we usually spot 2 very distinct types of coders attempting this exact exam. First up, we've got Dev Alex. Now, Alex is incredibly fast at crunching raw data inputs, but he constantly causes memory leaks. Why? Because of poor, rushed analysis. Alex just skips over the intermediate steps to print the final answer as quickly as possible. And then on the other hand, we have Dev Sam. Sam is actually great at writing logical loops and showing all the steps, but entirely fails the syntax precision rules. Sam uses sloppy notation, and the Cambridge framework absolutely rejects it. Look, to get a top-tier grade, you have to merge the best parts of Alex and Sam. The Cambridge assessment framework strictly prioritizes deep, logical reasoning, what we call analytical depth, over just taking a superficial, broad guess at the final answer. When you're applying the quotient rule, for example, the examiner isn't just looking to see if you memorized some formula. No, they are running a full diagnostic on your analytical depth. Did you explicitly define your u and v terms? Did you correctly derive du dx and dv dx before plugging them into the master equation? Because superficial breadth is just throwing random numbers at the page. Analytical depth means treating your math like high-level software engineering. And so, the absolute crucial point to take away here is that presenting your data with these exact formatting conventions is entirely non-negotiable for success. If our friend Dev Sam is failing the syntax rules, this is exactly why. Think about proper headings, correct mathematical terminology, and crystal clear annotations as the literal comments in your code. They tell the examiner precisely what function you are executing at any given moment. If you drop a derivative sign or you fail to use brackets correctly when applying the product rule, you have essentially written a broken line of code. And guess what? It won't compile. Moving on to Section 2, theoretical architecture. You wouldn't write a complex program without understanding the system first, right? Same rule applies here. Our entire theoretical architecture rests on these core principles, and the examiners explicitly note from the source reports that candidates who successfully code cross-topic connections into their answers achieve significantly higher marks. But what does that actually mean for you when you're sitting in the exam hall? It means the product and quotient rules almost never exist in total isolation. You're going to need to integrate these concepts with coordinate geometry to find the equations of tangents, or maybe link them up to kinematics to figure out velocity and acceleration. You literally must establish causal relationships between the raw function you're given and its actual graphical behavior. Which brings up a really critical question. How do we extract the relevant data and select the right analytical framework in the first place? Well, before you even think about writing a single line of math, we have to systematically extract the evidence from the exam texts, the graphs, and the tables. We have to ensure our inputs are flawless. You need to run a quick visual scan of the problem. Ask yourself, is this a product of 2 functions? Is it a quotient? Does it require the chain rule first before anything else? Selecting the correct framework before you start calculating is going to save you from getting stuck in an infinite loop of incorrect math. All right, Section 3, the execution algorithm. We've got our inputs. Now we need the actual procedural loop to solve the problem. Okay, Here is your brilliantly simple deconstruct, solve, evaluate loop. This right here is your ultimate algorithm for literally any complex product or quotient rule question you will face. Step 1, identify the given information. Step 2, break it down into logical steps. Specifically, isolate your u and v variables immediately. Step 3, solve systematically using the clear notation we just talked about. Step 4, evaluate by checking for reasonableness. Basically, ask yourself, does this derivative actually make sense for the function provided? And step 5, justify your final output. Trust me, this is the exact loop that high-tier developers use to clear the examiner firewall every single time. When we look at a side-by-side comparison of a flawed script, like our hypothetical dev Alex's super vague response, against a highly specific logical framework response, it is night and day. You can immediately see how executing clear notation prevents those dreaded system crashes. We absolutely cannot afford to write spaghetti code here. A vague response just spits out this unsimplified, jumbled mess of variables. But the specific logical response, it utilizes comparative connectives, it shows the exact substitution into the quotient loop formula, and it simplifies the algebraic output step by step. It leaves absolutely zero ambiguity for the compiler, the examiner, to misinterpret. Jumping into section 4, debugging the top 3 mistakes. Let's look at the actual principal examiner reports to audit where student text blocks are failing. Welcome to the interactive beta testing arena. Okay, I want you to imagine a 60-second visual countdown clock ticking in your head right now as we extract the underlying trends from these specific examiner warnings. These are the top 3 syntax errors you must debug today. Error 1, vagueness. You need specific details, always. Error 2, poor formatting and presentation. And error 3, a complete lack of context. Look, if the question asks for the rate of change of a specific physical model and you just leave your answer as some abstract algebraic fraction, you completely fail the context check. To debug this instantly, we deploy a really handy variation of the POL syntax structure adapted specifically for math. Process, execute, evaluate, and link back to the context. Process the raw data. Execute the math, evaluate the result, and link it back to the real world. Follow that, and your logic error is instantly resolved. All right, halting the compile screen for just a split second here. Before we push this final patch to secure those maximum marks, you really need to optimize your system feed. Take a second to subscribe to Ace the Exams at @AceTheExams right now, and go ahead and turn on all notifications for our weekly system updates. We drop explainer patches exactly like this all the time, and you definitely don't want to miss a single line of code. Okay, plug back in. Resuming the hackathon. Finally, section 5, the method mark strategy. This is where we deploy the ultimate fail-safe protocol for your exam. I want you to think of this as your absolute safety net. The method mark strategy ensures that if you leave a clear, undeniable trail of your logic, the examiner will reward your process, even if a tiny arithmetic variable throws off your final calculation at the very end. It means that simply correctly deploying the product rule formula and substituting the right parts into it will earn you points, even if you totally mess up the final algebraic simplification. You are essentially getting paid for the architecture, for building the framework, not just for the final executable. And this quote from the source material? This is literally everything. Showing your work step by step is the critical patch that secures your grade. If you skip steps, like Dev Alex does, you completely bypass the method marks. Think about it. If your final answer is wrong and you showed 0 working, you get a 0. Hard stop. But if your final answer is wrong and you showed a flawless procedural framework, you capture the vast majority of the marks. It's a game changer. So to compile everything we've covered in today's session, here is your final code deployment. This is your high-scoring, fully optimized text string to take right into the exam room. Your cheat sheet architecture, number 1, show all your working steps to aggressively capture those method marks. Number 2, prioritize analytical depth over rushing to the end. Number 3, be totally ready to integrate cross-topic concepts like tangents and rates of change. And number 4, always run a final check on your formatting, your terminology, and your contextual relevance. So I'm going to leave you with this final, provocative thought. Are you treating your math exam like a random, chaotic guess, or are you executing an optimized, flawless algorithm? It is completely up to you, but it's definitely time to upgrade your approach. Make sure to subscribe to Ace the Exams at @AceTheExams. Hit that notification bell right now and drop your exact subject and level in the comments below so we know exactly what system updates to build for you next. Keep optimizing your learning, and I'll see you in the next masterclass. System log out.